Okay, welcome to the last session of the day. You're in the room for deep learning and PyTorch. So if you want to be in the room for intro to machine learning, that's the auditorium. And as with the last couple sessions, if you realize partway through this that you're in the wrong session, feel free to leave. I won't be offended. For this session, I am going to assume that you're at least passingly familiar with machine learning concepts. So I kind of assume, for example, that you know what cross-validation is and that you know why we have like a train and test data set. If that's all nonsense to you, you might think about going next door and watching this one later. Oh, and I need to make sure to record this. Oh, it is recording. Okay, great. Okay. All right, so this session is going to be on, it's nominally an introduction to deep learning, but it's really an introduction to PyTorch, which is one of the two really big deep learning libraries along with TensorFlow. How many of you have used PyTorch before? And people online, you can use the raise hand reaction and I can see it. Okay, so not a whole lot of us. How many of you have used TensorFlow before? Okay, a slightly different subset. TensorFlow and PyTorch are pretty similar, honestly. They have a lot in common. I do not use TensorFlow very much myself, but if I were going to try to describe them as in like big picture terms, PyTorch, for whatever reason, seems to have been adopted by academia. And part of that is because it's easy to very quickly iterate in PyTorch. TensorFlow seems to have been adopted more by industry, partly because it's a little easier to set up like strict requirements for things. And industry cares a lot about that because they want things to be very stable. We're going to talk about PyTorch because in my experience, it's the one that's used in academia more often, and also because I use it and know it, and that's the really important reason. But to start out with, I just want to point out, if you're in the Jupyter notebook or the Jupyter Hub, and you can click on this little folder to go to your home directory, and you go to the curriculum directory, there is a Benson deep learning directory here. And inside of here is an introduction to PyTorch notebook. Now, I am not going to open this notebook and I'm not going to use, I mean, I'm going to go through everything in it basically, but my hope is that you'll live code with me and not just copy and paste from that notebook because live coding is a lot better for learning. So I'm just going to create a new notebook here and I'm going to do everything in here. Okay, so in order to get to deep learning, we're going to talk about a few things and eventually arrive at some deep learning. And we're going to go through an actual example problem where we train a convolutional neural network to recognize some stuff. But we're going to have to take a little bit of a roundabout track there because there are a few concepts we need to introduce first. But just to start out with, we're going to start by just importing PyTorch, which is the module is called Torch, not PyTorch. So import Torch. And then we're going to say from Torch, import NN. Surprise, NN stands for neural network. It is the module in PyTorch that contains most of the stuff that's useful for creating neural networks. We're also going to say from torch.utils.data, import data loader. We won't get to this for a little bit, but I'll explain it when we get there. Data loaders are classes for feeding data into a model you're training. And then finally, because we are probably going to want to visualize some stuff, we're going to import matplotlib.pyplot as plt. And by the way, there's nothing in this tutorial so important that you shouldn't interrupt me if you have a question. People online, I can't tell if you raise your hand or anything for the most part, unless I'm paying attention. So please just interrupt and we can hear you in the room. Okay. So to start with, if you just imported Torch and you were starting to look at it, what your first impression would probably be that PyTorch is a lot like NumPy. And it is a lot like NumPy, actually. So for example, we might start by saying torch.zeros 10,3. That probably looks a lot to you like np.zeros, which I haven't imported NumPy, so this won't work. But if you ran np.zeros 10,3, you'd get pretty much the exact same answer as a NumPy array. Here, instead of array, it says we have a tensor. So Tensors are really the mathematical term for array. Like if you're a mathematician, you would call an array a tensor. Tensors, like a vector is a one-dimensional tensor, a matrix is a two-dimensional tensor, a number is a zero-dimensional tensor. A 3D image like an fMRI image or a structural T1 weighted scan is a 3D tensor or a 3D array. So tensors and arrays are basically the same thing. Tensor is just the PyTorch version. So let's go ahead and assign some variable u to torch.zeros 10,3. And I just want to demonstrate pretty quickly here that just about everything you're used to in NumPy is going to work for tensors. Not everything literally, but most things are going to work just fine. So we can, for example, get a slice of just the first column of u, and it gives us back a vector of just this column. If we want to do operations like u minus a half, that just like NumPy will kind of multiplex across all the cells in the array, works the same way. PyTorch does broadcasting the same way as NumPy. So if we wanted to, for example, subtract, so in NumPy, we could say something like u minus 1, 1, 1, and it would subtract that vector, or let's do something different, 1, 1, 2, and it would give us back -1, -1, 2 for every row. Now here in PyTorch, this is actually going to not work. So with NumPy, no problem with this. NumPy will turn that list into an array and it will work with it just fine. PyTorch doesn't like to do that, unlike NumPy. So with PyTorch, if you try to subtract a list like this from a tensor, it's going to say, hey, you need to turn that list into a tensor first. So let's do that. We can say u minus torch.tensor 1, 1, 2. And then it does do exactly what NumPy would do, which is subtract 1, 1, 2 from every row. Any questions so far? Okay. All right. Similarly, so in fairness, I think NumPy is a great library. I'm going to go ahead and import it now. And it kind of spoils us in that it's so flexible with things like this syntax. And in general, no matter what you give to the numpy.mean or numpy.sum function, it's probably going to accept it and deal with it in a reasonable way. And PyTorch just is not like that. So even if we create a NumPy array, and then we try to use torch.mean, it's going to give us an error saying, I don't even work with NumPy arrays. You literally have to give me a tensor for me to work. I wish PyTorch had made different choices about this, but this is the world we live in. And so we just have to be very careful about turning things into PyTorch tensors before we use them with PyTorch. For a NumPy array like this array A we created, there's a special torch function called from NumPy. And that will just convert our NumPy object into a PyTorch tensor. So that's sort of your way out of that. Okay. Suppose we have a PyTorch tensor like the tensor u we made earlier, and we want to convert it back into a NumPy array. I'm not actually 100% certain about this, but I think that under the hood, PyTorch just uses NumPy for everything. Regardless, it's very efficient at converting back and forth between NumPy. So we can say u.numpy here as a method, and it will give us back a NumPy array. However, and we'll come back to this in a little bit, you generally shouldn't just call u.numpy because PyTorch does some things with its tensors that NumPy does not do behind the scenes. And so it keeps track of special stuff, and we'll talk about this, but it's keeping track of data kind of behind the scenes. And if you just attach something, if you just convert something to NumPy, you can screw that data up behind the scenes. And so what we typically do instead is we say first u.detach, which basically takes our tensor u and detaches it from any of that backend stuff, which again, we'll talk about in a minute. And then we call NumPy on that. And that will always work and always be safe. Now I'll talk about this a little more when we get a little farther, but Sorry?
Is it like copying?
Detach? Not necessarily. So I don't think detach necessarily copies, but if it needs to make a copy to keep the data safe, it will. So sometimes, like in this case, our tensor U, we haven't used it for anything. It's not actually attached to the backend system. So I'm guessing that u.detach just returns U.
So, like, does it change you?
No, none of this changes U. Now, actually, this is a really good question. I am not certain. Let's suppose we say numpy u equals u.numpy, and then we say we're going to set all of the first column to be 1. And then we look at u. So if you just call u.numpy, it returns whatever the backend numpy array representing that tensor is. And so here when we changed that array to have 1s, we also changed the tensor. Now, I'm pretty sure that if we say do the same thing down here, but we use detach.numpy instead, and then we do the same operation. And then we print out, well, let's set it to 2 so we can tell the difference. Okay, no, I'm wrong. So when you use the .numpy method, it will give you back an array that actually still holds the data for that tensor. And if you modify it, you'll modify the original tensor. Wow, learn something new every time I teach this. Honestly, I don't convert between PyTorch and NumPy arrays very often, so that's why I wouldn't have known that, but that's cool. Okay. All right. So let's see, we talked about that. All right. So for the most part, any function you can call from numpy.numpy.log, for example, you can also call from PyTorch. So you can absolutely call torch.log on you, and it's going to run on your PyTorch tensor. Pretty much any sum, mean, median, std, all those basic NumPy functions have a PyTorch equivalent, and mostly they work the same way and have pretty much the same arguments. You sometimes have to check, but for the most part, they're very similar. PyTorch was definitely written to resemble NumPy as much as possible. Okay, so I'm gonna pause here. This is just kind of your very quick intro to like the interface of PyTorch, like the high level interface of PyTorch. Any questions on any of this or its relationship to NumPy before we start talking about optimization? Okay, great. So we're going to pivot now and talk a little about optimization, because everything we talk about that involves neural networks and convolutional neural networks actually involves optimization. So if you ever take a numerical methods class or an optimization class, they will go into a lot of theory, and we're not going to do that. We're just going to talk at a very high level about what optimization is. The basic idea behind optimization is you've got some function. You don't necessarily know what's in that function. For all you know, this function is like going up to the internet and downloading stuff and giving you an answer. The point is we don't know what it is, but we can give it an argument and get its value back. So we can always calculate y equal f of x for any x. If I wanted to know what the minimum value that function ever took was, one way I could do that would just be to pick a lot of values and evaluate them and pick out whichever one is the smallest. Am I making sense so far? Okay. That's a very inefficient way to figure out what the minimum is, and it may not even find the minimum, because if you're looking for like the minimum of x squared and you pick -1/2 and +1/2 and 1.5 and 2.5 and 3.5, and those are the numbers you pick, you're not going to find 0. So the basic strategy behind almost all optimization, not all optimization, but most optimization involving like real numbers, is to start with some guess, and then to have some method where you can make a new guess that's just a little bit better, and to keep doing that over and over again until you eventually find the right answer. So now I'm going to try, this is always a disaster when I do it, but I'm going to do it anyway. I'm going to try to draw using my mouse. So bear with me. So suppose we have a function like f of x. Ah, that's pretty good. Okay. And we're trying to find the minimum, but we don't know this is f of x squared. Sorry, x squared. We don't know. This could be any function. And so we're going to just guess. We're going to guess 2 or whatever. So we pick x equal 2 and we evaluate f of x and find it's 4. Now we just need a way to guess something slightly better than 2. Well, there are a lot of strategies for this. One of them is to pick something very far away, like -4, or -5 or something, and then try to gradually move the point you're picking closer to the minimum. A more common way is to say, well, it'd be really nice if we knew which direction this function was decreasing in. If we knew that it was going up or down, we'd know which direction a smaller value is in, right? Well, if we calculate the derivative of f at x, it's going to tell us whether the function is going up or going down. So if it's going up, we'll make the guess smaller. And if it's going down, we'll make the guess a little bigger. Without doing all the math, that's the basic idea here. We calculate the slope at this point. There's a great drawing. And we see that the slope is something like this. And so we take a little step along this slope and pick a new value. And then we repeat it, find another slope, take a little step along this slope and find a new value. And we just do that over and over again. And as we do it, we get closer and closer to the true minimum and we never reach the true minimum, but we just keep going until the difference is so small we don't care about it anymore. That's how most optimization works at a very high level. Okay. Any questions about this so far? Have I lost everyone, or is this okay? Awesome. All right, this is the basic idea behind optimization, and we're now just going to run through a quick example using PyTorch. Now, critically, if we're going to optimize a function and we don't know what it is, we still need to be able to calculate the derivative, right? Now, if I tell you it's x squared, we can all say, oh, it's 2x is the derivative, right? Because we all remember calculus. But if I don't tell you it's x squared, then we're going to have some other way to calculate the derivative. And PyTorch will do all that for you, and so we don't have to worry about writing that or anything. There's a couple ways it can do this. One way is to actually just, if I want to calculate the derivative at x equal 2, it just says, okay, I'm going to try x plus a little tiny number and x minus a little tiny number, and I'm going to calculate the slope between those. Alternatively, if you've written your function in PyTorch, it actually knows how to calculate derivatives from whatever you wrote. We'll look at that in a minute. It's kind of like magic, but we'll see it shortly. Okay, so let's do an example here. I'm going to define a function that we're going to minimize. I'm just going to call it func. It's going to be a function of x, and we're just going to have it return x minus 2 squared. And you notice that this function, this x could be a number, it could be a PyTorch tensor, it could be a NumPy array, it doesn't matter. This will work for any of those inputs. Okay, now we're going to make a PyTorch tensor, and it's going to contain our initial guess. So I'm just going to say 4.0 is our initial guess. And I'm going to add another argument here, which is requires grad equals true. Grad here is for gradient, which is just a multidimensional derivative. So this is basically, we're saying this x tensor, it requires a gradient. And what that really means is we're cueing PyTorch into the fact that later on, we're going to want to know what the derivatives of something in terms of x is. So we'll go ahead and make that. And then I'm going to say y equals func of x. Okay. And then I'm just going to print out y at the end so we can see where we are. Okay. So basically it says 4, but it's not just 4, it's a tensor containing the number 4. And there's this little thing here that says grad fun power backward 0. Don't worry about that. That's basically saying this value is connected to something that requires a gradient. That's what that means. And that's because we calculated it using something that requires a gradient. So now, if we say y dot backward, this is a method that basically says, hey, PyTorch, I want you to use an algorithm called the backward propagation algorithm to determine the gradient of y in terms of whatever tensors we used to calculate y that required a gradient. Now, in our case, the only tensor we used to calculate y is this x tensor. So what we're basically saying is, hey, PyTorch, go use the backward propagation algorithm to calculate the gradient of y in terms of x. And we don't have to tell it to calculate it in terms of x because it already knows, because it kept track of how we calculated y. So when we run that, it doesn't return anything, but it's now gone and calculated the gradient in the background. And if we just say, okay, x, what's your gradient? Oh, right, that is right. Because it's not x squared, it's x minus 2 squared. So it knew exactly what the gradient was at x. Does everyone understand that? How we got that? Okay. So now this is a very simple little example, but it doesn't matter how many inputs you have, or if, x could have been a 10,000 dimensional tensor, and it would have just very quickly given us back a 10,000 dimensional gradient for y in that case. So this is actually a very efficient system for calculating the gradients of things. And this is one of the main things PyTorch will do for you. Okay, most of this is not something you ever have to think about. Now, I wanted to explain this so that you kind of understood what all this was and why we're doing some of the things we're doing later, and why we have to train in loops and things, because we're using this optimization algorithm where we very slowly approach the correct answer by following gradients. This example is very far removed from an actual neuroscience problem, but in neuroscience, a lot of times what we have is we have some set of measurements we've made, like maybe we've done psychophysical measurements where we've sat someone in front of a computer and we've had them like answer questions for a bunch of questions. And then we come up with a model of, based on some parameters, what would we expect those measurements to be? And then we want to do an optimization where we figure out what the parameters of the model are that match the data. That's also an optimization loop. It's just that instead of this being func of x, we're saying func of some parameters, and then instead of x minus 2 squared, we're saying something like predictions minus measurements squared. How far are the predictions of the model from the measurements?
Maybe we should use something other than 4.
Other than 4, is that too confusing? Okay, yeah, let's do like 10. So now it's 64 because, so at x equal 10, we have x minus 2 is 8 squared, and wait a minute.
8 squared, 64.
Yeah, no, that's, oh, right, yeah, y is 64, of course. That's why I'm confused. Yeah, the gradient is 16 because it's 2 times 8, which is the gradient of x squared. Yeah. Okay. Okay. All this is a little bit abstract. We're going to do something a little more concrete next. But questions so far? Okay. Okay. So the last thing we're going to do before we start building an actual neural network and dealing with actual data is just to kind of show how the optimization loop would look here. So basically, we would say something like x equals torch.tensor, just like we did before. 5.0 requires grad equals true. And then now in PyTorch, whether you're optimizing just one function or a model or a neural network or a convolutional neural network, we're going to start by making an optimizer. So optimizers are PyTorch objects that just manage the optimization process for you. So in this lesson, we're going to use, I'm going to say optimizer equals torch.optim.sgd, which stands for stochastic gradient descent. It's one of the most common optimizers out there. It's basically just a gradient descent optimizer where it follows the gradient. The stochastic has to do with how it gives data to the algorithm. We can talk about that later, but it's not really very stochastic. It's really just a gradient descent algorithm. And we give it a list of all the things we're going to minimize. So in this case, we're just minimizing x. So we're just going to say stochastic gradient descent optimizer. We're minimizing x, and we have to give it a learning rate. So the learning rate is basically when we calculate the derivative and we find out, okay, the derivative here is 8 or whatever, or 16, we could take a step of 16 in that direction, or we could take a step of half of 16 in that direction, or like basically, if the gradient is steep, we want to take a bigger step because the function is decreasing faster. But basically the learning rate is saying how much of the gradient do you want to follow? Like how quickly do you want to, how big are your steps going to be as you converge towards the solution? And the reason this is important is because, and it's important for all the minimization we're going to be doing today, but basically, suppose we're minimizing this function f of x squared just as an example, and we start here, and we get this gradient, something like that, and we take a really big step, and we take such a big step that we end up over here. Now our gradient is even bigger in the other direction, and if we take a same size step, we're going to end up even farther away. Right? So if our learning rate is too fast, we're actually not going to converge on a solution. If our learning rate is too slow, we will converge. It's just going to take a really long time. So picking a learning rate is actually, I wish I had good instructions to you on how to pick a learning rate. They're kind of, it's a little more art than science. You kind of have to try several learning rates and see what works. Typically, you want your learning rate to be substantially less than 1. We're going to do just 0.1 here. I believe it's just the fraction of the gradient length that you're going to move. But basically, smaller numbers means slower convergence. Bigger numbers means faster convergence, but more of a chance that you overshoot and get farther away. Okay, we're now just going to say for step number in, and we'll just do 40 steps here, range 40. The first thing we do is run this function optimizer.zeroGrad. Now, the reason we have to run this zeroGrad is because you might recall from calculus that gradients add. So if you have f of x squared plus f of x to the third, the gradient is the gradient of x squared plus the gradient of x to the third. So in these algorithms, this grad object that gets attached to the actual variable, as the backward propagation algorithm works, it will add things onto the variable as necessary. And so everything else we do here doesn't necessarily assume the gradient is 0. If I just lost you, don't worry too much about it. The basic idea is we need to reset the gradient so that when it does the next gradient calculation, the old gradient isn't still there. Yeah.
I'm a bit confused with the communication in some ways, like, like your optimizer is taking one argument that is x, and x is a tensor. But I mean, you might always complain that but you optimize is a function, so you that's an array like thing. So I'm a bit confused with the when it's being optimized. And if x is the tensor, like what is the function being optimized there?
Yeah, so the function we're going to put down here in the loop. But basically what we're telling the stochastic gradient descent optimizer is that this is the variable we care about that's being optimized.
Okay, those are data to be used in the function to be optimized.
Exactly. Yeah. So it is a little bit of a weird notation, but this is what PyTorch needs to know at this time. Yeah. Okay. We're now just going to say loss equals func of x, our optimization variable, and func is what the function we're actually minimizing. And loss is just what we typically call the error or whatever in these kinds of in these kinds of optimizations. All right, and then I'm just going to very quickly have a print statement here that basically says step number. I'm not going to make this fancy. I'm just going to say step number float of x. That's what prints out as a number instead of a tensor, and then float of loss, just so we can kind of see as it's going what's happening. And then we're going to do exactly what we did up here for y. We're going to say loss.backward. And then tell the optimizer to take a step. And the optimizer will manage all of the gradient descent parts for us. We don't have to worry about that. That's all part of the optimizer. And then at the end, I'm just going to print float of x and float of func of x. Okay, I'm just gonna run this. All right, so starts out with a pretty high loss, but you can see right away that as it goes through steps, that number is getting closer to the actual minimum. And this loss is getting smaller and smaller till somewhere around step 25 or 26, it's down to 10 to the negative fifth or so. And by the time we finish, it's got 2.003, or 4, which is pretty close to the true minimum, which is at 2. So we only did 40 steps. It was pretty fast. This is the basic idea of how these work. And the reason we're doing this with this very simple example is because this is pretty much the same loop we're going to use when we optimize our convolutional neural network. It's not going to change very much. What's going to change is what we tell it the parameters are and what our function is. But everything else, this is how you do optimization. Yeah. Backward? Yeah. So here we calculate the loss, and it gives us back a PyTorch tensor, which has that loss value. And then the optimizer needs to know the gradient of the function in terms of x. And loss.backwards just says, PyTorch, go use the backwards propagation algorithm to calculate that gradient. And it basically propagates from loss. It realizes that loss was calculated using x because PyTorch keeps track of that in the background. And we'll automatically go from loss to x and put the gradient on the x.drag. Does that make sense? Big picture here is that PyTorch will track all these gradients behind the scene. You need to do a few things here, like tell it to calculate them, but for the most part, you don't have to worry about them. As long as you're using PyTorch functions to calculate whatever you're doing, PyTorch can figure out what the gradient is all the time. Do you have a question?
Sorry, so when you say loss equal function x, x is the torch and the PyTorch object.
Yep.
The func is just a function.
Yeah.
We return a PyTorch object that has the function inside it in some way.
So yeah, so let's unpack this a little bit, because this is a good question and it comes with some confusion. So when we call func of x down here, x is a tensor that requires gradient, right? So it comes in here and it calls x minus 2. That's the first thing it's going to do. So minus is actually a method on the PyTorch tensor. And so what gets called is x dot like underscore sum underscore, it's some hidden function. And it passes it 2. And PyTorch says, oh, okay, I'm subtracting 2 from this tensor. I'm going to make a new tensor. I'm going to calculate the results. And then also I'm going to keep track of the fact that this came from x, and that the expression was x minus 2. Now, suppose that was the end of the calculation. We didn't square it. What would come back is this loss tensor. And when we call loss.backward, it would say, hey, what was I calculated from? I was calculated from x minus 2. Well, the derivative of x minus 2 is known. It's just 1. And so it would be able to put 1 in the graph for x. Does that make sense?
Yeah.
Yeah.
It doesn't depend on the step number.
It doesn't depend on the step number. It just depends on what you're calculating here.
So we need the loop.
So yeah, so the loop is just like do this over and over again, and every time take a little step and then start over and zero the gradients and make another step and follow the gradient descent again. Yeah. Yep.
Learning rate is mathematically, it's not dx. It's about the gradient, not the x.
It's about the gradient of y in terms of x.
Right.
Y in terms of x. Yeah.
But it's like a horseshoe.
It's a proportion.
Like when we go back, then can you show the results?
Down here?
Like it doesn't, the x doesn't change by 0.1.
No, it's so this is multiple, like the learning rate is used with the gradient. So whatever the gradient is here, it's going to like, I don't remember exactly what this does. I think it like finds the length of the gradient and then multiplies that length by 0.1 or something like that. But
So, yeah, I guess what I want to ask is, so like X can be an arbitrary number or
Mhm.
like, but 0.1, like the absolute value of LR is not important because it's a proportion.
Yes, yeah,
Okay.
yeah, right, yeah, okay. Yeah, learning rate is like, what's the fraction of distance we could travel that you want to travel
Okay.
in our step, something like that, yeah. Okay, other questions?
Not a question, but like whenever you like, can you not point to and just use your cursor because I can't see when you point to the screen?
Totally, sorry about that. Yeah, I'll and if I do it again, just remind me. Okay. All right. So again, these are fairly abstract examples. Let's actually look at a real example now, and we're going to start by loading in a data set. So this data set has already been, we don't have to do anything fancy. It's just basically saved in the shared drive. So we're going to start by saying train labels, comma, train images equals torch.load. So just like NumPy has a save and load function, you can save and load PyTorch data using the PyTorch or torch.save and torch.load. And we're gonna give it /home/Jovian. That's our home directory, /shared, /data, /Benson-deep learning, /mnist_train.pt. And then we're going to have one optional argument here, which says weights only equals true. And then we're going to have another line that's actually the exact same. I'm just going to copy it even, except we're going to say test labels and test images. And we're going to load mnist_test.pt. Has anyone used the mnist dataset before? Okay, so mnist, well, we'll look at it in just a second. This is a well-known machine learning training data set for like testing out models and things like that. Basically, what we've just loaded in are some tensors. So if we look at train labels, it's a tensor of integers is all it is. But if we look at train images, that's a fairly large tensor of data. And in fact, let's look at the shape. So it's 60,000 by 28 by 28. Let's look at train labels.shape. 60,000. So we've got 60,000 examples here. And on one hand, we have a set of labels, and on the other hand, we have a set of 28 by 28 images. So let's just plot one. Plot.imshow train images 0, just the first image. Ooh, that is a bad one. Let's do 10. That's not very good either. Anyone know what these are yet? Yeah, okay. They're handwritten numbers. Some of them are easier to read than others. Oh boy. There we go. There's a 3. Okay. They're all just images of handwritten numbers. Did you have a question?
I'm having trouble getting the URL. Would you be able to put in the Slack?
Yes. Let me just copy these 2 lines. And I'll just put that in the deep learning Slack. Okay. So the task we're going to do here is we're going to train a neural network to look at one of these images and figure out what the label is. What is it an image of? And notice this is train image 12. It's clearly a 3. If we look at train labels 12, it better be a 3. Yeah, it's a 3. Okay. So we've loaded in the data, but we actually need to tell PyTorch about this. We're going to tell PyTorch that we have a data set of these data. So we actually need to make a class here. I'm going to call this MNIST dataset. And it's going to inherit from torch.utils.data.dataset. So earlier we loaded in, we imported torch.utils.data.data loader. We haven't gotten there yet. This is a data set, not a data loader, but we're making a class that is basically represents a data set of examples for training. We really just need to define 3 functions to define a PyTorch data set. The first one is our init function. So this init function is just going to take images and labels. It's going to be like the simplest init function ever. Self.images equals images and self.labels equals labels. We're going to have a getItem function or method. All that's going to do is return a tuple, self.images of k and self.labels of k. And finally, we're going to define a length method. And it's just going to return the length of self.labels. The whole reason we're doing this is because PyTorch, when it deals with data sets, it wants them in this particular format or it wants them defined in this particular format. And so we just write a little class that follows its format. And then we can say train data equals mnist dataset. And we pass it train images, train labels. And same with test. Test data equals mnist dataset, test images, test labels.
Quick question on define.
Yeah.
What is the significance of the 2 underscores?
Okay. These are called dunder functions. I don't know who named that, but the basic idea is that anything that starts and ends with 2 underscores in Python is sort of like a hidden Python method. And so, for example, when you call len on something like this, the list type has an underscore len function defined that returns that 3. And so what we've done here is we've said, okay, these objects should work for length, and getItem is for like when you want to do data set k like this. So let's just walk through that. If I now say length of train data, it's going to call this function here and return the length of self.labels. If I say train data 12, it's going to pull out the 12th image, which we should be able to plot and see that 3 that we were looking at a second ago. Oh no, sorry. The function we wrote returns a tuple of the images and the labels. So we need to say m comma label equals training data 12, and then we can plot the image.
Thank you.
Yeah, no problem. Okay. Questions so far? All right. So this is kind of like boilerplate. This is code we need to write to tell PyTorch about the structure of our data. And we're going to need to use this because when we get to training the neural networks and stuff, we're going to need to use special classes that load batches of data into the training model batch at a time. And we don't want to have to write those ourselves. We just want to write this little interface and have PyTorch take care of the rest. But we'll get to that in just a second. Okay. Okay, so let's go ahead and set up what we call data loaders. Like I said, pretty much anyone who trains convolutional neural networks especially, you're training on images usually, and you can't hold that many images in memory at once. And so especially with a lot of these bigger CNNs, which are trained on like sometimes millions of images, you need to be able to train on batches where you get a certain number of images and you do some training steps, and then you get a new set of images and you do some more training steps. And even though we can fiddle these images in memory at a time for our example, PyTorch doesn't expect that, so it needs you to write like a data loader that can give you batches a little bit at a time. Additionally, when we're working with neural networks and neural network-like models in PyTorch, it has an expectation about the data, and what it wants is for us to have the data arranged so that our first dimension is the number of items in a batch. And our next dimension is the number of channels in our images. So when I say channels, traditional images have 3 channels, R, G, and B for red, green, and blue. These are just 1-channel images, but nonetheless, we need the shape of our tensor to be something like batch, comma 1, comma 28, comma 28. That's how PyTorch expects our data to arrive to its models and things. Okay, so what we're going to do is we're just going to pick an arbitrary batch size that we're going to work with for the rest of this notebook. I'm just going to make it 64. Batch size is another one of these things that really shouldn't matter in terms of like, whatever batch size you pick, you really ought to get about the same result after your training. But it can speed things up or slow things down a little. It depends a little on the model. We're not going to worry about it too much right now. 64 is a fine batch size. It'll be fine. Okay, so now we're going to make a train data loader. And the data loader is the object that manages these batches. And all it really needs is a data set. So we're going to say data loader, which we imported earlier. Train data, and we tell it the batch size. And then we do the exact same thing for the test. Oops. So I'm just going to copy and edit. Okay. So that gives us data loaders. We're not going to deal with these data loaders very much. We're just going to pass them off to PyTorch to deal with. Hopefully. Okay. All right. We're now finally ready to make a neural network. I know it only took us 45 minutes to get there, but a lot of boilerplate in PyTorch. That's because there's a lot of things it can do. All right, so we're going to make a new class called, we're just going to call it neural network. And this is going to recall that earlier we imported, whoops, you don't have to do this, we already did it. We imported this neural network module earlier. So we're going to use that now. And we're going to have this neural network class that we're making inherit from the neural network.module type. NN.module is Python's base class for all neural network adjacent kind of models. And it's actually a really great class, but let's talk more about it after we've gone through an example. Okay, for a module, sorry, someone have a question? No, I'm hearing things. Okay, for a model like this, we just need to define 2 things. The first is the init function. And I'll punt on what we're going to put there. We'll come back to it in a second. The second is a forward function. And it takes an argument x as well as the self object. So the forward function is the function that actually calculates the model. So x is the parameter or the parameter tensor. And this forward function just needs to return whatever the model calculates. Okay, so how do we set up a neural network model? And let me back up here a second and just talk about what neural network models are about. I'm assuming everyone knows what a neuron is, but the basic idea behind neural networks that were inspired by neurons is the idea that neurons have some set of inputs from other neurons, and they sort of calculate like a weighted sum of those inputs and then decide whether to fire or not based on that weighted sum. That is pretty much what a neural network is. It is a set of inputs to some unit which has weights on all those inputs. So for example, let me kind of draw an example here. We've got our neuron here. Oh boy, let me try that again. We've got a neuron and it's got inputs of various kinds. And each of these, so this is maybe X1. This neuron has a weight for this X value, and this has a weight for this X value, etc. And all it does is it basically is going to sum up X1 times W1 plus X2 times W2 plus X3 times W3. And it's going to say, is that sum, greater than some value? And if so, we're going to fire. Now that's what a real neuron does. Now a neural network actually will typically add up those, x1 times w1, x2 times w2, et cetera, and then output whatever the sum of the weights and the values are. So this is just a really simple little computational unit that basically does a weighted sum. But weighted sums are just linear systems, and we don't need to go into the whole linear system thing, but because this weighted sum is just a linear system, this is, if you just chain a bunch of these together, you can have a very complicated linear system, and complicated linear systems with lots of parameters can estimate anything. And so that's part of why neural networks work as these very general models, is because with enough parameters, you can estimate any function by just kind of summing up weights and values. Okay. Questions on that? Okay. So, all right. So we don't want to deal with the internal details of setting up a bunch of different neurons with weights and things. Rather, we want PyTorch to take care of most of that. So we're going to use PyTorch's internal kind of stuff. So we're going to start by writing this init function. The first thing we're going to do is call super.inits, because PyTorch needs to initialize its stuff. Then we're going to add, we're going to go ahead and say self.stack equals, and we're going to have an nn.sequential object. Neural networks are typically organized into layers of neurons, which all calculate their outputs and then go on to the next layer. And the outputs of this layer form the inputs for the next layer, et cetera, just like honestly, in real neural networks. And so we often conceptualize neural networks as layers of filters on things. And that's especially true with convolutional neural networks, which we'll get to next. But for now, basically, sorry, I don't want to point. The idea is that when the X input comes to this model, we're going to run a computation on it, and then we're going to take the output of that computation and run another computation on it, et cetera. And we're just going to let the values kind of cascade through these layers of the network. So we're going to put those layers in this sequential operator, or the sequential type. So we're going to start with nn.linear. nn.linear is the name for a basic neural network unit layer, because neural networks are basically linear systems. So that's why we call them linear. And this linear type just needs to know a couple things. It needs to know how big its input is, how many neurons are coming in which our case is 28 by 28, because that's the size of our inputs. So since our images are 28 pixels by 28 pixels that we're trying to train on, that's the input, and we're going to just flatten those and give them to the first layer of the neural network. And then it needs to know how many outputs it should produce, because we can have any number of neurons in this layer. We could have 1,000 or 1,000,000 neurons if we want, and they can all have independent inputs from the image and produce their own outputs. Does that make sense to everyone? Okay, so we're just going to say 512 as a number of outputs. Okay, then we're going to have another layer called ReLU. ReLU stands for rectified linear unit. That is a really fancy name for, we're going to take everything below 0 and set it to 0. That's all that layer does. And if you're wondering why we would want to put something in a neural network that does that, the best explanation I can give in a short amount of time is that it's kind of analogous to an if statement. As information is flowing through this network, it gets to a point where it says, oh, if you're less than 0, we're going to change you entirely to 0. That's sort of like an if statement that operates on the rest of the neural network. So it's a little bit like a way of having a brain. So that's not quite the right analogy, but regardless, these rectified linear units are very important for a lot of these networks to work. And they're very simple. After that rectified linear unit, we're going to put another linear operator here. And we're just going to have 512 to 512. So we're going to take 512 inputs and produce 512 outputs. Then we'll have another rectified linear unit. And then we're going to have nn.linear. And we're going to take those 512 inputs and make 10 outputs. And that's going to be it. Now, anyone want to guess why? Oh, well, not pointing. Anyone want to guess why we're producing 10 outputs? Yeah. Exactly, yeah, so, we want there to be, we want to get an output that is a 10-dimensional vector. Now, why do that instead of have that the neural network just produce one output that should land on either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9? Yeah.
Wouldn't that be because it would bias values to numbers closer to the thingy algorithm?
I think that might also be true, but I was going for something much simpler, which is that we're trying to produce integers, and this is going to produce real numbers, and trying to train a neural network to produce integers out of real numbers is very difficult. Without going into a lot of detail, that just ends up being very hard. And it's also just like here, what we're basically going to do is we're going to ask the network, here's 10 buckets, put a high number in whatever bucket you think is right. And put low numbers in everything else. That's what we're really training the network to do here. That's just much easier for this kind of system to do than to come up with exactly 9 or exactly 1 or exactly 4 or whatever. So this is sort of a strategy to make training work faster and easier and generally just work. Okay. Oh, there's one thing I forgot to put in here, I'm realizing. When we get this X value, it's going to have 28 by 28 pixels, and we need to flatten that to a vector before it works with these neural networks. So the first thing we actually need to put here is a flatten. And that flatten is smart. It knows about batches and channels, and it will just flatten the rest of things. So it handles the batches and channels just fine. Okay. Since we've said, oh yeah, go ahead.
So this is just like this sequential, meaning like you do this one by one, that's one after the other.
Yes, yeah. But
What's the,
well, so it's a little tricky because we're setting up a pipeline. We're not the calculation doesn't occur here. We're just setting up the pipeline that knows how to make the calculation. And then in the forward function, we'll do the calculation. Is that your question?
yeah, I just missed that part, but and then linear 5 to 12, 5 to 12, that line, what was that?
This is just another layer of neurons that take 512 inputs and produce 512 more outputs. Yeah.
Each one is a layer.
Yeah, exactly. Each line in this the sequential is a layer.
Yeah.
Pretty predictive.
What's that?
That's pretty predictive.
Yes. Yeah, these are all fully connected layers. Any other questions? Okay. So because we put everything in this sequential object, our forward function is really easy. We're just going to return self.stack of X. That's it. Okay. And let's just print the model. Well, let's make a model first. Model equals neural network. And then I'm going to print it. So you notice that PyTorch knows about all these steps. Like it's all set up to like model things as sequential layers of filters. So it knows that we're starting out with a flatten that we put up here, and then a linear that we put here, etc. And it's going to keep track of all that for us. Okay. There's just a couple more things we need to worry about before we're ready to actually train this neural network. The first is we need to decide what our loss is. So when we get this prediction out, what we're going to get is 10 numbers. And the idea is that some of those numbers are going to be high and some of those numbers are going to be low. Yeah, let's leave it at that. Now we know that we have a label 0 through 9 that matches those buckets, and PyTorch has a specific kind of loss function built in called the cross entropy loss. It's a very commonly used loss for these kinds of labeling problems, where you've got a set of buckets and a set of numbers that correspond to those buckets, and you need to train the model to produce one of those buckets based on the label. That's exactly the problem we're solving here, and that's exactly what the cross entropy model optimizes for. basically, basically the cross entropy is very similar to the dice coefficient, if you know the dice coefficient. It's sort of like how much did your inputs overlap your outputs correctly, or what fraction of overlap was correct. We're not going to worry about it too much here. We're just going to say loss function equals nm dot cross entropy loss. And then one other thing, we need to redeclare our optimizer. We're going to once again say torch.optim.sgd. But this time, what we're actually optimizing over is not like X, it is the parameters of the model. So we're going to just say model.parameters. And LR equals 0.05. Okay, so what is this doing here? Well, model.parameters will always, as long as you've written a PyTorch module, it will give you back whatever the parameters of that model that's represented in that module are. What I think is kind of hidden here that's not obvious is that those parameters are inside of these linear objects. So when we say linear with 28 by 28 inputs and 512 outputs, it comes up with a set of random weights inside, and those weights are the parameters of the model. So as we train this model, we're actually training those weights to produce better answers in this calculation. Does that make sense? Okay. Fortunately, we don't have to figure out what those are. The model knows it. We just tell it we're using those model parameters. This 0.05 for the learning rate, you can try a different learning rate if you want. I played around with this before the lesson, and if you pick 0.1, it will diverge, like it will get worse as you go. So you have to pick a pretty small learning rate with this one. Again, it's a little more art than science. You just kind of make your learning rate small enough that it works, but not so small that it's slow. Okay. All right, so I think at this point we're ready to start training the model, finally. So we're just going to make up our loop, much like we did before. We're going to say for step number. And then we're going to say capital X comma Y, and I'll explain why in a second, in enumerate train data loader. So hopefully most of you have seen the enumerate operator before, but if you haven't, enumerate just gives you back tuples where you've got an index and then whatever value like that. So this step number comes from the enumerate, the X and Y come from the train data loader, and this is just the image and then the label. In fact, let's have a better name. Let's call this image and label. That's a little more descriptive. Okay, and this data loader will give us back batches. It'll give us back 64 of these at a time. And it'll give it back in the shape that with the like batches, channels, rows, columns that PyTorch likes. Okay, we're just going to say pred equals model of image. So this is our predicted label. Now, of course, it's not actually a label. It's a tensor of 10 values, and the real label is wherever the number is highest. And then we're going to compute our loss function. So loss function of pred versus label. So this cross entropy loss, like I said, is specifically made for exactly this kind of optimization problem where we're producing buckets, and we want the bucket with the highest number to match the label. So we don't have. This is a very easy way to set up this problem because that's exactly what this cross entropy loss calculates, is how good of a prediction did it make given the label. So this may seem very simple, but that's all we need to do there. And this loss value will be large when it's guessing the wrong label and small when it's guessing the right label. Okay. We can then say, oh, I forgot something. Optimizer.zeroGrad. We always have to start out by zeroing the optimizer gradients. Then we can do loss.backward down here. and optimizer.step. Okay, and then I'm gonna add, you don't have to add this if you don't want, but if you want to see something printed out, I'm gonna say if batch number percent 100 is 0. So if batch number mod 100 is 0, then we're gonna print, we're gonna say loss current equals loss dot item. This just extracts a single number, and then batch or whip step.
When did you define batch number?
Sorry, that should say step number, my mistake. It's this, yeah. Step number times the size of the batch. And this is basically what's the current image we're on, or how many images have we seen. And then I'm just going to print loss. I'm going to use some fancy f-string stuff to print just 7 digits of a floating point number. And then I'm going to say current, again, print 5 digits of an integer, and of 60,000 total images that we're training. So this is going to say basically the loss at this point in the loop, whatever the loss is, and then it's going to tell us how many images have we seen so far. And we're going to loop through the whole data set. So we're going to go through all 60,000 images in this training loop. Before I run this, any questions? Did that all make sense, or should I go over some of these lines again? Okay, so just to review, we're gonna loop over everything in our training data set using this data loader, which gives us batches of 64 images at a time, which we decided up here somewhere when we said batch size is 64. We're going to start by zeroing our gradients for our optimizer. We're going to calculate the prediction of the model, which initially is going to be just random noise, because those weights that we created are just randomly initialized. But we then calculate the loss or the error in the prediction it makes using this cross-entropy function. And then we do a gradient descent step to try to get to a better prediction, or a better set of parameters for predicting. And then we'll print out a little information as we go. Okay. Oh, I did something wrong. I forgot to put a quote in a close parenthesis. Let's try that again. Okay. So a few things right away. First of all, the loss initially is fairly high, but it quickly gets smaller. And it gets smaller, but it doesn't only get smaller. Eventually it goes up a little bit. And that's to be expected in a lot of these kinds of problems. It's part of the reason is because you're not training on the whole data set at once. You're training on batches. So an individual batch, so after the very first batch, the model's going to take a little step, and it's going to get better at predicting specifically that batch. But the next batch might be completely different. Like the first batch might have been all 3s, and the next batch might be all 7s. That's very unlikely, but it could happen. So it's not guaranteed that every batch is going to be have a smaller error than the last batch, because the batches are different. Now, if we went through this loop many, many times, we'd expect that it would eventually get smaller and smaller and converge on, like, over the whole data set, the error should converge on whatever the smallest number is. But regardless, it sometimes goes up, and that's not a surprise. However, it did get a lot smaller than when we started. So let's just see how it did. Okay, I'm going to write a bunch of matplotlib code, and then I'll paste it over to the Jupyter Hub or to the Slack channel in case anyone doesn't want to follow all this along with me. But I'll narrate and go fairly quickly here. So I'm going to start by creating a new figure with a set of axes. We're going to have a 2x2 grid of images, and I'm going to make this about 6x6. That should be fine. Okay. And then I'm going to say for X, or let's say images labels in test data loader. Now I'm going to use the test data loader because I want to test this on something it wasn't trained on. We trained using the training data sets, and now we're going to use a completely different data set to test it so that we cross-validate our losses. Okay, now this is just a bit of a hack, but I'm going to say if np.random.rand is less than 0.9, continue. I'm doing that because I want every time we run the cell, I want it to generate a new set of images. And this is just a way of saying kind of randomly keep going until you until some random event and then print those images. Okay, we're going to make a prediction using our images. And we have to do something special here because remember the thing I said earlier about how when you pass something to a PyTorch model, a module specifically, it wants everything to be in batches by channels by X or by rows by columns, whatever. So we need to add a unitary dimension here at the front. So we're going to say none. And then the rest should be fine. Then we're going to say label equals torch.argmax of prediction. So our prediction produces numbers. The biggest number indicates the bucket with the right prediction. So if, for example, we have 10 buckets and they're, -1, -2, 0, 5, and then a bunch of zeros or something, and we ask for the argmax, it's going to tell us wherever the biggest value is. So if it's in the 5th bucket, it'll give us back a 4 because we're a zero-based language. And that's the correct label. Did that make sense? Let me just draw that because I think that didn't make sense. So we've got these buckets that go up to bucket 10 or bucket 9. And this is bucket 0. And this is just part of a tensor. And the network, if it sees a 2, for example, it's going to put a really big number here, and all of these are going to be little numbers. And then when we say argmax tells us the index of the biggest value in this tensor. So it's going to tell us whatever the network thinks is the most likely digit for this particular example. Okay, so that's how we can get the label out. Okay. And I think at this point we can say, we're going to say ax.imshow of I have an error in my sim code. Okay. We're going to say ax x, y in zip, and we're going to zip across the flattened axes our images and our labels. I'm going to disambiguate here. I'm going to say predicted label. And this will just, because we only made 4 axes, it's going to go through 4 images and then stop. It's not going to do all 64. So this is just going to print out 4 kind of random images and the predictions that the model makes. And we're just going to say ax.imshow x, and then we're going to say ax.set title, and we're going to say estimate is predicted label, and true is this y, the actual label. And turn the axis off. Oh, I think I forgot a name here. Well, okay, so we're having the issue we're having is something about the shape of the images. So I'm just going to have to debug it real quick. I'm going to print images.shape. So this is 64 by 28 by 28, which is actually kind of what we expect. Okay, I think I know what happened. We already have the batch here, so the batch is fine. We just need to add a channel. Ah, there we go. Okay.
What's the channel?
Sorry, channels is like, for a lot of images, channels are RGB. So there's 3 channels. But these are just these are like black and white images. So they just have one channel. But because they're just black and white images, so just to be a little clearer, we have 64 images and then we had 28 by 28. So 28 by 28 is the rows and columns. Now, if this were an RGB image, it would be 64 by 3 for RG and B, 28, 28. Since we only have one channel, we often don't have we just ignore that one dimension. But that's why we need to do this none thing here, is to make sure we have a channels dimension, because PyTorch expects us to have a channels dimension. Okay, so we have another issue here, which is that Torch is coming up with really high numbers, like 112. Yeah, exactly. We didn't put an axis here. So it's attempting to make this prediction over everything, over the whole, all the batches and everything. So I think we need to say axis equal 1. Actually, I think in PyTorch we call them dimensions instead of axes. No? I'm just guessing here, so I'm probably going to get it wrong a few times. Let's just take a look. Thread labels dot shape. Thread labels dot shape is actually 10. The air jumping out to anyone else?
I did the axis.
This works with axis.
I'm gonna try. I don't know.
So I think it might be flexible about whether you call it an axis or not, but I think it's still not going to work correctly. Yeah. Okay, so
But see when you have things, but one thing they easier.
sorry, what?
Can you blame space thread maybe?
Yeah, good idea.
It's not missing.
So this should be argmax.axis1. Oh, I see what's going on. Okay, the problem, yeah, I screwed up something much more simple. Okay, so we do want to calculate the argmax over this 10, the dimension of 10, because we want to know which of the 10 buckets has the highest value. So it should be axis or dim equal 1. But we need to pass these labels into this function here and print out the predicted label for this particular image in the batch. There we go. Okay, yeah, my mistake. Okay, I will copy all this and stick it in the Slack channel now, in case you want to copy it now that it's working. Well, I lost my, there we go. Okay, so looks like it's doing pretty well. Here we got, this is clearly a 4, this is clearly a 9. Now I guarantee if we run this a few times, we're going to find examples where it doesn't do very well. And you notice it's coming up with different examples each time, although these are all correct. So it seems like our model is doing pretty well. Wow. All the times I tried this before the lesson, it honestly produced pretty bad results pretty often. So whatever, every once in a while things don't go right until you teach it, and then they only go right when you teach it, but usually it's the other way around. Okay, so clearly, whatever else we can say, this is doing a pretty good job of predicting the correct labels for this network. And it's no surprise, we're actually creating a pretty complicated model. If you think about it, we have all these weights that turn these 784 into 512. So we've got many thousands of weights here, and we have many thousands of weights here, and also, 5,000 some weights here. So there's a lot of weights. This is actually a really big linear system we just built. But we did it using PyTorch, and so it was all very fast and easy. Well, relatively easy. Okay, this is just a neural network. It is not a convolutional neural network. And this is taking a little longer than I expected. So I'm going to talk about convolutional neural networks and adapt our network here. And rather than writing a new one, I'm just going to edit the code to be a little faster. But basically, so this is a very simple neural network. Convolutional neural networks are inspired by the human visual system. The basic idea, the reason I say that is because you can think of our visual system as taking something like an image as input and running it through a series of filters. And the very first kind of set of filters that our visual system does is it extracts information about like angles and edges and lines and boundaries and things. And it does that by essentially looking at every local part of your image of whatever you're seeing and performing some little calculation over it. And then the next portion and the next portion of your input. It's sort of like, how many of you have done like Gaussian smoothing, where you take an image and you smooth it with a Gaussian? That's exactly the kind of thing convolutional neural networks do. You're basically just taking at every pixel, you're multiplying the neighborhood by a Gaussian, and then the new value of the pixel is whatever that neighborhood is. Okay, I'm going to open this up real quick because I have a link that explains what convolution actually is in here. Okay, so the idea behind convolution is you have, oh, and I bet everyone online can't see this. Let me share again real quick. Okay, you've got some matrix, and then you've got a kernel, which is a little matrix. And you're basically just taking the kernel and you're sliding it over the bigger matrix, which is your image. So this is like our input image. These are the weights inside of a convolutional model. And the idea is that you slide this little matrix along the big matrix, and you calculate like the dot product of the little matrix with the overlapping part of the big matrix. And that becomes the cell of your new output matrix. So we've got basically this little matrix is like a filter, and we just kind of move it along and produce a new image that's based on the original image, kind of filtered by this kernel. Does that make sense? Okay, so in convolutional neural networks, we basically replace these like linear neural network things with convolutional operators. So I'm just going to leave some space here. We don't, since convolutional neural networks operate on actual 2D images, we don't need to flatten anything. So instead, we're just going to start out right off the bat with neuralnetwork.conv2D for 2D convolution. We don't have to write any of the code that does the convolution. That is one of the great things about PyTorch, is that it's got all that under the hood. And the reason, just really briefly, the reason convolutional neural networks have taken off and have been such a big deal is because convolution is a really efficient computation. We can very efficiently calculate a convolution. And so it's a very efficient way to process a bunch of images or a big image with some kind of filter or kernel. Okay, convolution kernels just need to know how many image channels are in the input. In our case, there's just one, and how many are in the output. And then it needs to know how big the kernel is. So in that example we just saw, the kernel was 3 by 3, very small. But we can make a kernel any size. And we're just going to use 3 for this one. And then we give it a stride. The stride, this example has a stride of 1 because we're moving the little kernel by 1 pixel every time. If we had a stride of 2, we'd move it by 2 pixels every time. If you increase your stride, your output matrix gets smaller because you have fewer positions you line it up with, and thus fewer pixels you produce in the output. Also, if you increase the size of the kernel, this matrix gets smaller because typically you don't allow it to hang off the edge, and so you remove like a pixel on either side of the image when you do the convolution. So, this is going to, this convolutional layer is going to have an output that is a 2-channel image that's just a little bit smaller, 1 pixel on each side than our original image. Okay, we're going to put a few more of these. We're going to put a rectified linear unit again. We're gonna produce even more channels this time. We're gonna make this an 8-channel image, and we're gonna use a kernel size, whoops, of 5 and a stride of 2, and that will reduce the image's size quite a bit, but make it thicker. We're basically reducing the amount of spatial dimensions in the image, but giving it more channels. We'll do that We'll do that again. Stride is 1 this time. We'll do one more rectified linear unit, and then we'll do one more convolution. 8,10. This time we'll use a kernel size of 7 and a stride of 2. And you can just trust me that I did the math beforehand to make sure that we get 1 pixel with 10 dimensions as the output. You can see that we're going to get 10 channels out because I've got a 10 here as the output channels. But these kernel sizes and strides gradually reduce the number of pixels in the rows and columns until at the end here we've got just 1. And so we're just going to end by having a flatten. And that's the end of this convolutional neural network. So that's all we had to do to turn this into a convolutional network. 9, we're almost out of time, so we're just going to train this and then see how it does. Going to make a new optimizer here. And I'm just going to run the exact same training loop. I believe it will just work. No such luck. Okay. Okay. I believe this is just an issue with the image shape. Yeah. Okay. So we need again to give this a none dimension, which creates a unitary dimension right there, so that we have a channels dimension, because we previously were just 64 by 28 by 28, and we need 64 by 1 channel by 28 by 28. Okay. Now you notice this is a little slower. That's because convolution is more expensive than the calculations we were doing before, but also it's at least achieving some pretty low losses. It's doing a little better than our last one. Okay, so let's see how it did. Now our last one did pretty much perfect, so I expect this to be pretty similar. Yeah, these are just fine. Okay, so we've trained a neural network and a convolutional neural network. Now, I went over a lot of stuff very quickly in this lesson, as you probably all were aware. Part of the point here is that I wanted to get you exposed to kind of the breadth of what you need to know in PyTorch to do these kinds of problems. This is pretty much it. There's a lot more in PyTorch, but as far as the basics of making a deep neural network or a convolutional neural network, all this code has been borrowed from actual research projects I do where I train convolutional neural networks to try to identify functional brain regions based on neural anatomy. That's what I research in real life and outside of NeuroHackademy, and this all basically came from those projects. So this is actually how you set up these models, and there's a lot of kind of things to know about PyTorch. But once you kind of have the basics down, it's actually a very easy system to work in. And we didn't have time to really talk about this, but one of the great things about these module objects is that if I now want to take this network I built and make it a component of some other network, I think that the first thing this network needs to do is to predict the handwriting in this image, and then it needs to go do more calculations with that prediction. That's something that PyTorch is made to do. So it's really good for kind of mixing and matching models you've written or other people's models or things like that. One last thing I'll say is that PyTorch also has a bunch of built-in models. So if you've ever heard of a ResNet, ResNets are a very commonly used model for doing exactly what we just did, where we're like trying to classify an image into some category. And you can basically just say, it's not torch.resnet, but it's like, I think it's in the torch vision module, which is like a companion module of PyTorch. You can basically just say, torchvision.models.resnet, and it will give you back a fully trained ResNet, and you don't even have to like do all this coding to set up the internals of it. So there's a lot of these tools are becoming very easy to use. And I would encourage you, if you're interested in this, to just kind of take a look around the pytorch.org/tutorials section. There's a lot of really good tutorials on the PyTorch website. And most of it is really, it's a little arcane, but it's not that hard to use. Okay, any questions on anything? Yeah. Okay, so the reason that bug happened was because originally the first thing we did was we had a flatten here. And so it didn't care if we had the channels and rows and columns rates. But in this, since we're doing a 2D image convolution, it needs to have channels there, or it will get confused as to whether the 28 is, like, it's not sure if we're trying to give it 28 channels and we screwed up our image, or if we screwed up our channels and gave it a 28 by 28 image. So well, what I had to do was down here, let me just put this back, and then I'm going to break. Whoops, I meant to print image.shape. So as we iterate over our data loader, it gives us back batches of images and labels. Our batch size is 64, so it gives us back 64 images that are each 28 by 28. But PyTorch needs us to have a channel dimension here. And so when I said image : none, that's a shortcut to create a length one axis as our second axis. Have you seen that before? This is a same is true in NumPy. If I make like a matrix like this, and I want to add a unitary dimension in the middle, I can do that, and it turns the shape into 3, 1, 3 because I put a none here. That makes sense? Okay. Other questions? Yeah.
There were two numbers that I wasn't following where you got them
Mhm.
from. So 512
Yeah.
for the number of inputs, and then the 60,000 of the thing at the end. What are the motivation for those two numbers?
Yeah, so 60,000, it went by very quickly, but we saw it at the beginning when we loaded in our images somewhere here. The length of our data set was 60,000. So there were 60,000 examples in the data set. That's why it said that. The other one, where did I come up? Now I deleted it, which was probably ill-advised, but originally I had linear with 28 by 28, 512, and then linear 512, 512. So that I just divided that number from the ether. It's nothing special. It's just how complicated do you want the internal model to be? How many parameters in the linear system? So if we had picked 100 parameters, it would still have all worked, but we would have had a much simpler model, and it might not have done as good a job of predicting the numbers. We could have picked more parameters, and it would have taken longer to train and been a more complex model. But the only important part is that any given layer of the neural network has the same number of inputs as the last layer produced as outputs. Yeah, good question. Any others? Yeah.
Is that kernel just once?
Sorry, what?
Is it kernel that we convolute? Is it just once?
Every one of these conv2D layers has its own kernel.
And the values in the kernel is determined by
They're randomly initialized. Yeah. So the idea is that every time we train this, so when we create a new neural network model here, it randomly initializes all those internal parameter weights as sort of a random guess as to the start point of the model. And then as we do the optimization, it's taking little steps to try to make those parameters better for the model.
So kernel values depend on weights.
Yes, the kernels are made up of weights. Yeah.
Okay.
Yeah. Sorry, there's a little jargon there, but the idea is that each element of these little kernel matrices, each of those is a weight. Other questions? Okay. Yeah.
If you had already trained models and in some places, like
Mhm.
a good place, whatever, like you bought that and you train with like another set of specific data.
Yeah. So that's actually something people do pretty commonly, is that so like there's existing ResNets that have been trained already, for example, on great big data sets. And we can kind of deduce that they've learned something about the structure of images just because of that great big training. And so if we then have some very specific data set, like I want to predict the location of V1 in a bunch of people based on their brain anatomy, we can take that network that's already learned some general things about images and do a little more training on our specific data sets. And the idea is that that general training should help. And it generally does in my experience. No. All right, thank you, everyone.
Maybe you're.